Welcome to the lecture on ray tracing within the course of computer graphics at KAUST. This lecture is describing a core technique of rendering, meaning providing or generating, synthesizing an image out of 3D scene by a technique called ray tracing. This is a particularly important technique because we will, in our first assignment, essentially implement this technique in its simplest form. And then over the course of the lab, we will be advancing this simplest technique into more advanced features of ray tracing. Ray tracing as a rendering technique is a conceptually very simple technique, and it's a so-called image order technique as opposed to object order techniques, which first would sort of iterate over the objects. In natural scenery, a illumination will be first cast from the light source and will be passing onto objects within the scene, and then these light rays will be interacting and reflecting and refracting through these objects, and finally they will be projected, or they will be cast towards the eye or the camera, where either the eye or the camera will sense the intensity of the light and understand the geometry of the scene based on this light propagation. In ray tracing, we perform a different direction, which is starting from the eye, and we are casting the rays in the direction from the eye towards the scene, and at some point we are connecting these rays with the light sources in order to evaluate how much is particular part of an object illuminated or in shadow. It is called image order technique because we start from an image, we cast the rays from an image, and then for each pixel as an element of this image, we evaluate the corresponding viewing ray or viewing rays in order to find out what is the particular color of this pixel. This is as opposed to object order techniques, which are different in this approach, where first we will be iterating through all the objects in the scene and trying to sort of project them onto the viewing plane. And we will be discussing these type of techniques as rasterization techniques because they are very popular implementations in the graphics hardware. The advantage of ray tracing is that most of the photorealistic effects, which are then making our scene in graphics indistinguishable from the real scene, are somehow inherently already included in the ray tracing, while in the object order techniques there is always a new and another approach how to integrate a certain feature. For example, in the rasterization, we would normally have no shadows. Therefore, there is a special technique in order to perform the shadowing of the scene, so that the scene contains shadows and we can understand the scene geometries better by the presence of shadows. These shadows are already present in ray tracing, so we do not need to add another technique on the top of the standard rendering technique, so to say. Ray tracing is also supporting techniques such as perspective, occlusion, reflection, or global illumination. So there are various levels of complexity of ray tracing, but they all follow the same basic principle. Now we can see the ray tracing in this short pseudocode that it contains few sort of stages of its algorithm. So first, we need to compute for each pixel a viewing ray. And once we have this ray, which is a line in space, then we are calculating intersection of this ray with objects in the scene. This is the second stage. And once we find intersections, and in case our objects are opaque, then only the first intersection, so the closest intersection to the eye, because that one will be finally projected on the on the particular pixel. Once we have that intersection, then we are calculating how much is this pixel illuminated or how much it is in shadow. And from here, we can continue calculating, for example, secondary rays. So if this would be the normal at this particular position, then the secondary rays will be calculated how much this light is reflected from towards the eye eventually. So let's start with the individual techniques. Before that, we, as a historical note, need to state that ray tracing is similar to what artists have been doing since Renaissance, where they discovered linear perspective and they were connecting when they were drawing a particular scene, three-dimensional scene, then they were often using a straight wire to connect the object with the positions in canvas or with a particular point, which was the eye point. And at this position, then they will investigate where is the canvas sort of intersected, and so that they understand of the perspective projection principle. If we are dealing with just a pinhole camera, such a linear perspective will be also the way how the scene will be sensed by either human or a machine when a camera will be observing a particular scenery. But if in case we are including an optical element such as lens into the light propagation towards the sensing element, then the geometries might often change. So, for example, a fisheye lens will generate a distortion which will then violate the basic condition of a linear perspective. So, and the linear perspective is basically saying that everything what is having straight lines in the 3D scene will be mapped into straight lines in the image. So this is a linear perspective. These lines might no longer be exactly at the same geometric arrangements to each other, but they will remain straight. What I mean is that if we will have parallel lines in the scene, and these parallel lines will be then projected on the scene, they might likely no longer be parallel, but they will still be straight. When we are talking about projection, we can choose from several different types of projection. A conceptually simple and very popular for technical drawings or applications in engineering or healthcare imaging is the parallel projection, because the parallel projection not only preserves the lines being straight, which are straight in the scene, but it will also keep parallel lines will remain parallel, and there is no perspective for shortening, meaning that objects will not be becoming smaller under the projection when they are more far away from the eye point or from the viewport. Now, if we are talking about the parallel projection, there are several ways how we can project an object. And one way is if we have a very simple scene, like here, we can see this cube, and this cube is aligned with the coordinate space. So let's say this would be z, this would be y, this would be x. Then if we are just projecting the object onto the viewing plane such that the viewing plane normal is aligned with the projection a direction, then we are talking about orthographic projection. Even more so, if we are if this projection is aligned with one of these axes within the scene, like for example the z-axis here, then we are talking about axis-aligned orthographic projection. And if we have not such an alignment, but still the viewing plane normal is used for the projection onto the plane, then we are talking about orthographic projection. If the direction of projection on the viewing plane is different from the normal of this viewing plane, then we will be talking about oblique projection. Still a parallel projection, but from an oblique angle, so to say. We can see the second type of projection is the perspective projection, which no longer preserves the line parallelism if two lines are parallel to each other in the object space. They will no longer be parallel to each other in the image space. However, they will still remain linear, as we discussed is the condition for the linear perspective. Again, here we can talk about an oblique or non-oblique perspective projections in case when our viewing plane is used as or its normal is the direction of projection of objects onto the viewing plane. If the normal of the viewing plane is not identical with the projection direction, but there is an angle between the projection vector and the viewing plane normal vector, then we are talking about oblique perspective views. Why we are mentioning these oblique perspective views? Well, in case of virtual reality applications, in order to create a stereo pair for each eye, in order to create an immersion effect, we would need to generate oblique perspectives instead of non-oblique perspective projections. So therefore, their application is used in such a context. I have just explained the difference between the oblique projections and the non-oblique ones. The parallel projection first is important for mechanical and architectural blueprints. The object space lines correspond to the image space lines in the sense that they are both parallel, and very importantly, the size and shape of objects are preserved. So if I am measuring some size of a certain object under the parallel projection, it will be preserved this size on the image plane. The perspective projection is the way how we perceive the world with our eyes. Therefore, if we want to create a naturally looking scenery, then perspective projection would be necessary. The perspective itself is a depth cube. We in arts the definition of perspective is also additionally using additional scene elements which are interplaying with the perspective, such as, for example, the horizon line. And any line in the space which is parallel to the, or which is which is aligned with the horizon plane, but of course can be displaced, then such lines will be meeting in such lines, if they are parallel in the object space to each other, will be meeting at the horizon line at the so-called vanishing point. So various parallel lines in the object space, if they are parallel to each other, they will share the same vanishing point where they will meet on the horizon line. We can see it on this image on the right hand side. Now, after the introduction of the perspective and perspective and parallel projections, let's have a look how we can now generate a race which would correspond to either perspective or parallel projection. Our array we will define as a parametric line. And now, let's say, first for the perspective projection, the ray will start at the point E, which will be the eye point, which is here in this graphic. And then we will connect it with a sample point in our viewing plane, point S, and we will, by that, define the viewing vector for this particular sample, which we will then try to intersect with the elements in the scene. Now, this object, this vector is defined ES by the difference between the position of the point S and the point E, and it is parameterized by the parameter T as a parametric representation of a line. So if the T would be equal to 0, then the point which will be defined on the line PT, P0 will be E. If the T will be 1, then E minus E will cancel each other out, and the point on the line will be the S. So normally we will be looking at the scene with such a viewing ray for T values which are higher than 1 until some maximal value, which we will define as the maximal possible depth of the scene. Or we can define it from 0, from the eye point, to this maximal depth. And in such a case, we will also be investigating the scene sort of in front or between the eye point and the canvas. So either we can imagine that the canvas is something like a window through which we are from the eye point looking out, and we are just observing the scene outside this window, or we are having this canvas just as a proxy, and we are really interested in all elements which are in the scene, starting along the viewing ray from the eye position. That will be when our T will be varying between 0 and some very high number corresponding to the maximal depth. Now we can see that with increasing T value, we are in the parameter, we are also reaching more far and far in the scene. So this condition holds if T1 is smaller than T2, then PT1 minus E is smaller than the PT2 minus E. So the distance from the I point for T1 is smaller than the distance for T2 parameter. Therefore, this is very important because when we will be evaluating the visibility along the particular ray, we will be intersecting several objects in the scene, but we will be only interested in the intersection which is closest to the viewpoint, especially if we are dealing with non-transparent objects. If we are dealing with transparent objects, then the situation would be a little bit more complicated. So how can we define this race? Or how can we have as an input the I point, so we know that. And in order to define the ray, what we would need more would be the samples on the viewing plane. So how can we get these samples? We assume that we have some viewing direction, which will be the direction W. Normally, this should be this direction W will be the parallel to the viewing plane for achieving the non-oblique views. So we have also this viewing direction, and then we also have something like an up vector. So we want to orient the image in such a way that it is not the projection is not turned upside down. You can imagine it as if I am taking a photo with a camera, then this camera I want to have oriented so that the top of the camera points towards upwards. If we have a coordinate system like XYZ, where X, Y, and Z will be defined in this way, then the Y direction, Y vector, would be a natural candidate for an up vector. However, this y vector will often be not perpendicular to our viewing direction vector. So our viewing direction vector will need to be additional vectors will need to be generated. For example, the up vector for the camera, which is then somehow close to the seen up vector, but not exactly parallel to it. So how can we generate that? We can see that the vector W we can compute from the points on the viewing plane on the screen as S minus E, and then normalizing it. Or actually, this is the vector W is not pointing towards the viewing plane, but away from the viewing plane in order to maintain a right-hand coordinate system. Now, if we have the up vector of a scene, which we had y before defined on the previous slide, then if we create a cross product between the w and y, we can create the u vector, which will be then a vector which is perpendicular to the w and perpendicular to the y vector as well. And then once we have the u and w vectors, we perform the calculation of the v vector, which is the cross product between the u vector and the w vector. All these vectors would need to be normalized so that we are having a orthonormal coordinate basis. These two vectors u and v will be very important for defining the sample points in our image. We will show how. So first, let's have a look at the parallel projection, where we have our viewing direction. Let's say this viewing direction is defined through the normal of the viewing plane, and so the viewing direction we know it's the minus w in our coordinate system, and then we have the eye point. For parallel projections, we often say that the eye point is in the infinitely far away from the viewing plane. That's why the lines, the rays are parallel to each other. But it would not be practical if we want to, for example, create parallel projections in an indoor scene. Then the eye point will be outside, and we will be only see the house, so to say, only from outside. Therefore, we place the eye point into the center of our viewing plane. And then we define for our viewing plane the borders of our image, which we want to render. So we will define the left, right, bottom, and top offsets from the eye point. And if we want to have a symmetrical representation, then we will often have the eye point symmetrically far away from the left and right and from the top to bottom. Once we have this set up, we also have to take into account what is the resolution of our of our final image. So this resolution will be defined by the nx and ny. How many pixels do we have in the x and y dimension? And then we can define the pixel spacing, how far away are the pixels from each other, by the following formula. The r minus l divided by nx. This will give us the pixel spacing between the individual pixel in the x dimension. Very analogously, we can find out the pixel spacing in the y dimension. Now, for the coordinates of the individual pixels, pixel positions, the starting positions of our rays, we would need to compute the offsets. And this can be defined by the multipliers u and v, which are the scalar values, and they are defined in the following way, where the I is the iterator in the x dimension, starting from 0. So I goes from 0 to nx minus 1, and j would go to from 0 to ny minus 1. And with this iterator, we will address in the position of individual pixel centers in our image. So note that there is some kind of a magical value of 0.5 here. This means that we are just a half of a pixel width offsetting our pixel position, even the zeroed one, from the border. So even if we will have defined the I equals 0, the position will not be entirely on the L position, but it will be L plus very small 0.5 divided by nx times, so 0.5, the pixel spacing, as we have it defined here, and you can see it also here. And then the same holds for the y. So the first pixel, which is, let's say, the bottom left, or for example, will be addressed with I equals 0, j equals 0, and but it will be not entirely on the L and B positions, but slightly offsetted by the half of a pixel size. And Then we are iterating with I and j, and with these iterators, we are covering the entire area of the image with the samples which are corresponding to the individual pixel positions. So for the parallel projection, we already have the viewing direction, and we have the viewing the ray origin. So here you can see that we are having the ray origin defined by the point E. So we will start searching for the position here, and then plus U vector with a certain offset. So either this way or this way, which is the offset is determined by the scalar u, and plus v. So with another vector, we are defining how vertically the position of the particular pixel is. So this is again the scalar, which we have computed from the previous slide, and this is the vector along which we are then searching for the exact position within the viewing plane. For the perspective, we have essentially a similar situation, but there is the difference is that the eye point is not just part of the plane, but it is outside the plane and at a certain distance d from the viewing plane. And this distance d is also sometimes referred to a focal length. Changing the distance d towards smaller, our rays will be more apart from each other, the variance of the rays will be higher, and if the d will be larger, then we will obtain more and more parallel projection like looking projection. The u and v are computed in the same way as for the parallel projection. So we are iterating between L and R position with this iterator and with this pixel spacing as it was defined on the previous slide, couple of slides back. And then once we have these, then the ray origin here is very simple because that will be kept constant for the perspective projection. And this will be E for all the rays. And the ray direction will, however, change for each pixel because the rays are no longer parallel to each other in perspective projection. And it will be defined as the vector ray direction will be defined as minus d times w. So imagine we are going from the point E by the direction minus d times w. So this will be going to the center of our projection plane. And then again, the offset u along the direction u within the image plane will tell us where the pixel is located and in the horizontal direction, and the v will define where the pixel is located in the vertical direction for all the pixels within the range from iterating between 0 to nx minus 1 or 0 and ny minus 1. So with this, we have ray origin and ray direction, which only defines our ray. And therefore, we can define our parametric equation of a line which defines our rays. Both for perspective projection or parallel, the principle of this parametric line will be the same. So we will have some starting position, and then we will have some ray direction. Now, imagine that we have the perspective projection because the E is the eye point here, and then we have the ray direction and parameterized with a certain parameter T. Now, we have a let's say, the second stage, after we have set up our rays, we are interested whether we can intersect these rays or one particular ray which we are currently processing with the objects in the scene. So now we will be starting iterating over the objects in the scene. And these objects can be defined analytically, like for example, a sphere can be defined as a particular object in the scene. So now the sphere, imagine we have the sphere defined in implicit with an implicit formula fp equals to 0. And this is generally a valid approach. In every time we have an implicit definition of an object in the scene, what we can simply do for the point in the scene, which we are sort of evaluating whether it is equal to 0 in this function, which means that it's on the surface of a particular geometric object, we can simply enter our point from the parametric line. And then this will be the terms which we are putting into the into the uh, um, into the implicit equation, as we can see it here. And then we are not evaluating whether or not it is equal to 0, but we are evaluating for which t value this function will result into 0. And once we find a particular t value, then we will find the intersection of the ray or of the line with that object. So let's have a look at the example of the sphere. The sphere is defined through a radius and a sphere center. The sphere center has the coordinates xc, yc, and zc. Here is the standard formula for the sphere, where we have the x coordinate offsetted from the center squared, y coordinate of a point offsetted from the center square, and z coordinate offsetted from the center square minus r squared, the radius square, equals to 0. So if we have a surface point having the coordinates x, y, and z, this sum of these individual coordinates will sum up to the r square, and r squared minus r squared will be 0. In another formulation, a vector-based formulation, we have here the point minus center point, and the squared minus r is equal to 0. Now let's put instead of the point, the definition of our line here, line points here, e plus td, both for each terms here, and then let's try to find out what is the t value which will intersect us, under which t value we will intersect the sphere. Now let's have a look at the sphere. If we have a sphere here and we have a ray, one ray, R1, will not intersect the sphere. For other ray, R2, we will just touch the sphere at exactly one point. And for another ray, R3, we will intersect the sphere at 2 points. If we have a look at our implicit sphere representation after we have entered there the formulation of our line points, we can see that simplifying this formulation will result into a quadratic equation where the t is the variable or the unknown which we are looking for. And we have various terms associated in this quadratic equation. So for example, this term here will correspond to the a, and this term here will be corresponding to b, and this term here will be corresponding to c. So if we have our standard ax squared plus bx plus c equals 0, a quadratic equation, then we have something very similar here. For that, we can use simply the evaluation, which is based on this just x12 equals minus b plus minus square root of b squared minus 4ac divided by 2a, which is the formula for evaluating the roots of a quadratic equation. And here we simply will enter the corresponding values onto this formula. So we can see here minus b is here, and then b squared minus 4ac is here. So this line should be a bit longer, and divided by 2a. Now you see the 2 is missing here, and the 2 from here is also missing here. But then b squared will be having here 4, and 4ac will have here 4 too. So just don't be confused by this formulation. We have simply taken out the 4 out of the square root as a 2, and then taking it out as the term for the entire nominator part. And in the denominator we have also 2, so we have simply got rid of the 2's. And that's how this quadratic equation solution is also shown in the book. So this will give us a t-value. If the t-value, so for example, if here the evaluation in the discriminant, if the value will be smaller than 0, this means that the roots of this quadratic equation are not real numbers, they have imaginary components, which means that it doesn't, geometrically, the interpretation is that the root is the solution is that the line and the sphere are not intersecting. If the discriminant will be equal to 0, so that would mean that our ray is exactly touching the sphere at one point. And if it will be higher than 0, then we will have two values of t resulting from this quadratic equation solution. Now, the t, which has the smaller value, will be the intersection of the with the sphere which first hits this sphere. So when the sort of ray enters the sphere, while the higher value of t will be the value where the ray exits the sphere. We are all interested in the value where the ray enters the scene, because enters the sphere, because that's the first intersection point. Then we get a particular t value, and then we can go back to our linear parametric equation and find out what is the particular point corresponding to that already calculated parameter t. And then we will have the intersection between the ray and the sphere. This way we can proceed with other implicitly defined objects, like for example ellipsoids or cylinders or cones, etc. But often we have our scene described as a triangular mesh. We are using triangular mesh as an approximation of a smooth objects where these triangles are approximating the surface, which is of course for the triangle planar, but with a high resolution triangulation we can create a very sort of smooth meshes with that. So often an outcome from a 3D modeling software will be a triangular mesh describing a certain object, like for example a landscape or a face of a person, etc. So here we can again come back to the parametric equation of our line, and we can also define the triangle first of all, whether the triangle is on the on is subset of a particular plane. So we can first calculate what is the intersection point with this plane. And this plane can be also, for example, defined in um, implicit form, but also we can have an parametric definition of a plane where we have the parametrization will be through beta and gamma. So remember from the lecture on math for computer graphics, we were using beta and gamma as barycentric coordinates. When we have our triangle defined by the vertices A, B, C, we can then parametrize the triangle positions, points, by offsets from the point A along two vectors, AB vector and AC vector, and their linear combinations through beta and gamma. If we want to have a triangle, a particular, um, if we want to have a particular point belonging to the triangle, we need to make sure that beta and gamma are positive and their sum is smaller than 1. Then this will be the constraint for the area within the triangle. Into this equation, we can then enter the beta and to find out the beta and gamma parameters and the t value of the of our uh, of our intersection point. And if all of these three values will be within a valid range, then we will have an valid intersection. So let's have a look at it at detail. We can create an linear equation system where there are three unknowns, t, beta, and gamma. Three unknowns, three equations, so we can solve the linear equation system, and then we will find out t, beta, and gamma. And this is what we will do. So here you can see that we have reformulated this linear equation system into a matrix formulation where we have put now the terms associated with beta to the left-hand side and also with gamma. Therefore, we would have, by subtracting it from the right-hand side, therefore, the xb minus xa has now turned into xa minus xb here, for example, from the first expression, and the same holds for the gamma. Xc minus xa is turning into xa minus xc here for the gamma. And then the xe, um, the coordinates of the I point are going to the right-hand side. So then the XA values are subtracted by the XE for the X coordinate and etc. for the Y and Z coordinates. So we have a linear equation system which we can solve in various ways. An attractive approach would be to solve it with a Cramer's rule by solving determinants. It's determinants which are reasonably simple because there are 3 by 3 determinants and we know how to calculate 3 by 3 determinants just by heart. For higher, larger sized determinants, this will be more complicated. And the Cramer's rule says that for each value which you want to calculate, you can calculate it by the fraction between so-called dx and for x and by d. So the determinant in the denominator here is the matrix as we had it from before. So you can see here the terms associated with beta, with gamma, and with t. And now the terms associated with, in the nominator, the terms associated with beta are replaced by the right-hand side. So here we have the right-hand side, but the rest of the matrix stays the same. So this is the Cramer's rule for calculating values in the linear equation system. And here we then can, once we have these two matrices, we can simply calculate the determinant by multiplying along the diagonal with different terms. This term will be multiplied by this term, and it will be subtracted by multiplication of this term with this term and this term, and etc. We are continuing with these two terms, and this term subtracted from these two terms and this term in order to find out the value of the discriminant in the numerator and then in the denominator. So you can find different ways of solving this linear equation system. The advantage of this solution, which I was just describing now, is that in the ray tracing, we would like to quit the calculation as soon as possible so that we do not need to compute more. And for example, if we will have our t parameter from the line only within certain acceptable range between t0 and t1, because for example, the previous intersections with other objects have already defined this range, and if this object will be behind, the intersection will be behind, let's say T1, then this is no longer interesting. Or if it's before T0, it's also not interesting because maybe this is behind, would be behind the I point, so it will be in the different direction. So, or it will be behind the viewing plane if we define this metaphor of looking outside the window. So here we have the first the simple calculation of the intersection with the triangle, where we compute t by this Cramer's rule as described in the previous slide. And if the t is smaller than t1, or it is bigger than smaller than t2, t0, and bigger than t1, then return false. There is no intersection test which would be interesting for us. If, however, we will be within the permissible range between t0 and t1 for t, then let's compute gamma. And if the gamma is smaller than 0, so it's negative, or bigger than 1, then again, stop the calculation because we do not want to waste the computational resources. We know that the point is not intersecting the triangle, only the plane, but at some other position. And then, but however, if the gamma will be between 0 and 1, then let's compute beta, which if the beta is then smaller than 0, or the beta is bigger than 1 minus gamma, then return false. And otherwise, return true, so otherwise the intersection with the triangle has happened. And we will know where did it happen because we will already compute the parameter t for our ray equation. This way, if we use the Cramer's rule, we can stop the calculation of these individual unknown variables at the time when we realize that certain necessary condition is not fulfilled and we do not need to compute any more further. If we would solve the linear system in some different way, then we might end up with more calculations. And imagine if we have a lot of triangles in our scene, the likelihood that the triangle will be actually intersecting with our viewing ray is relatively small, so we can benefit from this early calculation termination and gain performance in our rendering process. If we have not a triangle, but another planar polygon, we can have another strategy how we can evaluate the ray object intersection. So imagine if we have a planar polygon, meaning that even if the polygon has more edges or more vertices than just a triangle, 3, 4, or more, then but it's planar, we can simply calculate whether a point belongs to the plane by looking at the, let's say, if our polygon is defined by point P1 to P4, then if our point P somewhere, P is um, forming a vector with P1, which is orthogonal to the normal vector of our plane, then this point P will be in the plane. We have discussed it on the math lecture. Now, this is the implicit representation of a plane. And then we have the parametric representation of our ray here. And we can put them together in order to find out what is the intersection between the plane and the between the plane and the ray. Now we find out a particular t, hopefully, in case the ray will be parallel to the or orthogonal to the normal of the plane, then we will not find any solution. But if there is the line is not parallel to the plane, then we will find some intersection point. Now the question is whether the intersection point is inside the polygon. So, and here we will be using for such a planar polygon, and it doesn't need to be a convex polygon actually, we will use a trick to find out whether this point is within the polygon or it's not. In principle, we will imagine if we are now having this 2D case, which I have drawn to you, and the P indeed lies on the plane where our polygon is. If we will now cast a random ray which intersects goes through our polygon, let's say something like this, then if our point is inside, which is not in this case, then the number of intersections in one direction will be odd. If it's outside, it will be even. So here our point P is outside, and for this one ray which we have defined, there is an even number of intersections, which means that our point is outside. If we will have another point Q, which will be inside, and then we will cast a ray, then the amount of intersections with the polygon will be odd. So we will have here just one intersection in one direction, and that will mean that our point is inside this inside the polygon. To simplify this into 3D space, there is a simplification that we can simply project the point and the polygon onto the 2D plane. Hopefully the polygon will not result just into a single line, so that it will be sort of parallel the plane with other planes or x or sorry yz or xz planes. And so hopefully there will be some area of this projection on the projected polygon, and it will not be just collapsed into a line. And then we also project the point. So imagine in 3D, let's say we have somehow defined a polygon in space. here is our coordinate system, here is our point, and we are simply throwing all these points. We are like, let's say this is the P5, and it is having coordinates x5, y5, z5. Then the projected version of this point, so it will be projected here, P5 prime, let's say, will have the values x5, y5, and for z, it will be 0. So we simply just forget about the z coordinate for all these points. So by this, we will drastically change the geometry and the relationship between the distances, let's say, between the points. But what we will not change is whether the point which we are testing is inside the polygon or it's not. Within the 2D the projection onto the xy plane, this property will not be destroyed. It will be preserved, and we can find out whether in a simpler calculation, whether this point will be within the polygon or not on this projected version of it on the xy plane. With the same principle, odd number of intersections mean that the point is inside, or even number of intersections means that the point is outside. Okay, so we have a couple of examples of geometries for which we already can perform intersections. There are more to look at, and for your assignment for the simple raycaster, ray tracer, you will have other objects to intersect. So you can try to find out for a representation, analytical representation of other solid objects such as cones or cylinders, etc. Now, after we compute the intersection, we are interested what is the color of this intersection. So we would need to perform the so-called shading. Therefore, we are evaluating the shading based on some formula, which are an approximation of an physics interaction. And especially for matte type of surfaces, this is a good approximation of the light interaction in the way that and the principle is the following. So imagine that we have a certain illumination of a surface, and this illumination is under certain angle to the normal. So this angle theta is the angle between the normal at this surface position here and the vector to the light source. And the smaller is this theta, the stronger will be this illumination affecting the light source, affecting the illumination at this position. So the more, if the light source will be here, then this will be the strongest illumination. And if the light source will be here, it will be decreasing and decreasing, and here the illumination will be 0. So, and this can be modeled by a cosine term of the theta vector, theta angle, and which is the vector between n and L vectors, which are typically describing our scene. So for the illumination, we typically look at 3 vectors sort of emanating from the surface point, which we want to find the illumination for. One is the vector towards the viewer, the v vector. Another vector is the normal vector of the surface, and another vector is from the surface point towards the light source. And as these vectors are normalized, we can actually calculate the theta from the vector n and L. And these two vectors, from the light vector and the normal vector. In fact, we can directly compute the cosine term, and this one is the one which we are interested in. Remember, for the cosine, if the theta of cosine, that cosine theta is 0, meaning these two vectors, light vector and normal vector, are aligned, then cosine theta will be 1, and if they are perpendicular to each other, the cosine will be 0. So this nicely models our illumination relation between L and N. And this is the so-called Lambertian illumination, where the light intensity is calculated from the source light intensity and modulated by the cosine term calculated from the dot product of the normal vector and the light vector. However, imagine that the light vector, the vector to the light, might be actually bigger than 90 degrees, and then we will end up in a negative value. So the light will be actually behind the surface. So it should not be illuminated at all by such a light, that surface point, and therefore we have here this max function. So which takes either the term n dot L as a result, or in case this would be negative, it takes 0. So it clamps this cosine term to be coming from values between 0 and the n dot L scalar product, which is then multiplied by the illumination, the maximal illumination from the light source. And further on, it is weighted by some coefficient, diffuse coefficient, which is for now not so important, but it will gain its significance for along the go when we make a little bit more complicated shadings. This illumination model, keep in mind that it only uses N and L as vectors for calculating the illumination proportion. It doesn't take the viewing vector into account at all. So we can change our position of the eye point of the viewing direction, and the illumination will not change by this. And this is generally a valid approximation for matte surfaces, where even if we look at the object from a different directions, there will be no change in the illumination at that particular point. Here is the result of applying Lambertian illumination. As we described it, we can see that the light source is coming from somewhere like this, and it's illuminating our scenes, which we have previously calculated the intersection tests with. Please note that the clamping here is then resulting in these entire areas into 0 light, because there is the 0 of this from this max nonlinear function will be then reducing or eliminating the illumination to 0 for these points. For other points, we can see a smooth gradient in illumination between the directly illuminated points towards the ones where there is bigger and bigger angle between the normal vector at the particular position and the light vector. So exactly here, the dot product between the normal vector and the light vector will be 0, which means that the normal vector will be perpendicular to the light vector, while here the light vector and the normal vector will be aligned and parallel to each other. In the previous slide, we have seen the gradient, gray gradient behind the two spheres, which which was not very well defined as an object. Now, in this view, we can see that the gradient is actually a plane on which the two balls are placed on. And this is thanks to shadows in the scene, actually due to various light sources in the scene. So this is something what we will develop along with the ray tracing. But for now, the Lambertian illumination shading doesn't give us any possibilities to evaluate the shadowing. But we will come to that effect later. On the top of the Lambertian shading, we will also define a more complex shading model, which is often referred to as Blin-Phong illumination. So, and this model adds on the top of the Lambertian shading the behavior of materials which are more shiny. So we will add a so-called specular component to the illumination. The Lambertian shading will be responsible for the so-called diffuse illumination component, and the shiny specular component will be achieved by the specular formula. Now, this part will be based on the following observation. If we look at our scene and imagine that we would have something like an ideal mirror, if we would have a light source at a certain position, then what will be the strongest reflection of the light source? So if the light is coming from the direction minus L to the surface point, and then the strongest reflection will be according to the normal vector will be in this direction. So this will be the strongest reflection of this light, of this also specular highlight, which we will have for maybe not ideal mirrors, but for enough shiny materials. And the angle between the light vector and the view vector will be basically defining us how much is this, how strong is this specular component. So if the light vector and view vector are a reflection of one of each other against a normal vector, then this component will be the strongest. And the more they will be deviating from this reflection, the more this component will be smaller. We can also model it in the, so this was the formulation based on the light vector and the view vector by Fong. Fong is actually a first name of a researcher from Utah who has introduced this, this lighting model. So usually we use the naming from the surname, but in this case, Fong was the first name of the Vietnamese researcher. And the Blin later on reformulated the Phong illumination by introducing the so-called halfway vector. The halfway vector is a vector halfway between the light vector and the normal vector. We have here determined with the H. And the closer this halfway vector is to the normal vector, the higher should be this specular component magnitude, because it is ideally the halfway vector between light and view direction is aligned with the normal vector, is parallel to it, and the more it deviates, then the less and less specular component the surface point will have. You can see the calculation of the halfway vector here, where we simply add the two vectors and and then we normalize it. That's how we can get the normalized halfway vector. And also we can see here the extended illumination model, the Blin-Phong illumination model, where here we will have the illumination based on the Lambertian shading with the weighting factor KD coefficient, and here we will have the part of the specular highlight, which will then similarly to our function, max function, either deliver 0 or the dot product between the normal vector and the halfway vector, which effectively defines as the cosine alpha as shown in this drawing here. And additionally, this term is this max function is powered by a certain power, because sometimes we want to change the size and the crispiness of this specular highlight, and for this power function, this shininess exponent will be helping us to model the particular properties of a material. Now, if we are adding the view-dependent specular component into the illumination, we can see the difference on the sphere, on the green sphere, where we can see the specular component. And then we can also see right away how many lights are used for the illumination. So we see 3 light sources are actually forming 3 different specular components, giving us an impression that this sphere is of a shiny material, as opposed to the blue sphere, which is a more matte material, and that one is only for the shading is only the direction, the Lambertian component used. So now we know the illumination can consist of a directional specular component, the direction independent but surface normal or orientation dependent Lambertian illumination, and then we often want to have in a scene model the global illumination in the simplest possible way. So we assume that there is some ambient light which is uniformly distributed in the scene, and it serves as a minimal illumination of a particular surface. So this additional ambient illumination we will be modeling with this term Ka times the ambient illumination component. So here we can see the entire formula now for each light which is used for shading, and now we can model the material properties of our objects in the scene by changing the different coefficients of ambient, diffuse, and specular components. Now, this has been explained in a way which is somehow independent of the different of colors. Of course, our light sources can have colors. Our materials can have colors too, and therefore we evaluate such a light illumination for each color component independently. So first we will evaluate it for the red channel, for the green, and for the blue channel. We have also something called ambient occlusion, which is an ambient illumination model, which is, however, not entirely constant. And it's while it is not really based on the surface orientation, it is based on the neighborhood of the surface. So, for example, if our surface is having such a shape, ambient occlusion at this location will be occlusion will be minimal because this surface is exposed. But in this area, in this cavity, we can see that there is some kind of we are limiting the incoming light coming from all directions. Here we will be limited only to the light coming from these directions, and therefore all these components of the light, ambient light, will not be contributing to this illuminating this part. So we will perform some kind of evaluation of the neighborhood, how much of the neighboring surface is blocking, so to say, the visibility of the surface point to the ambient light sources around, and by that we will weight the illumination. So this illumination component can be either constant or can be weighted by the neighboring geometry occlusion factor. As we have been discussing the lights so far as having one light, but as the property of additive property of light holds, we can add arbitrary amount of light sources into the scene and evaluate the illumination of these light sources independently. So first we evaluate the illumination with respect to one light source, then with respect to another light source, etc. And then we simply sum up the illumination contribution from all light sources together. And that will be the additive approach, where we will be adding one light to the scene after another and increasing the illumination of the scene this way. So this is expressed here, where the light sources are then forming a sum, and each light source is, so to say, indexed by the index I, and the n is the number of light sources in the scene. We have mentioned that for proper perception of the scene, the notion of shadows is a key aspect. So how can we bring the shadows into the ray tracing? So far, remember, we have just landed from a ray onto a particular surface, which was the first surface which was intersected with that ray, and there we evaluated the illumination. But we didn't really check whether the object is directly visible by the light source or not. And in order to do that, we can calculate the so-called shadow rays. And simply at the position which we are evaluating the illumination for, we are connecting the light source with the position on the surface. Here, our light source is sort of infinitely far away. Therefore, these two lines are both the direction towards the very far light source. And for the point P, the light source is directly visible. There is no occluder between the light and the surface point P. So there we can perform the shading calculation. But for the point Q, there is, however, occluder in between, and that one will block the contribution of that light source to the surface position Q. So we should not perform the illumination there for the point Q from this light source, which means that our light source will be in shadow. And how can we find it out? Simply, we compute the shadow ray, which will be again a ray, but with a starting point Q, and its orientation will be towards the light source. And we will again, for the scene, compute the intersection test with objects. And if this intersection test results into a valid intersection, this means what? This means that there is a geometry between the light source and the point Q, which means that the point Q is being occluded. So, but only if there is no intersection, the intersection test returns false for all objects. This means that the point is not in shadow, as would be the result for the point P here. The point, the shadow ray, as we call it, is calculated for all light sources to find out which light source actually results in this in the illumination of this point. And by this shadow ray calculation, and then either skipping or performing the shading, we will indirectly generate these shadows through ray tracing. Please keep in mind that due to numerical precision, it is advisable to start the T parameter from the point P towards the light source, not from 0, but from some very small epsilon value, because sometimes due to numerical imprecision, it might happen that this epsilon, that the 0 will put the object sort of inside itself, and then there will be an intersection test evaluated with the geometry of the object itself, of the surface itself, and therefore we just go a little bit outside so that this numerical imprecision cannot happen. So this would be the t equals epsilon. Okay, so this is the simple way how we can generate shadows in the ray tracing. Moreover, sometimes we would like to model the color transfer or color bleeding effect between various objects. Just try to put on your desk a pen with a distinct color and observe that there is on this pen is somehow changing the color of the of your desk. If your desk is white, for example, then you will be able to see it. This is the so-called color bleeding effect because the light is being reflected from the object onto the surface of the table, which you are then seeing. And this we can model this in the ray tracing by the reflecting of our rays, viewing rays, which we have intersected our surface with. We can not stop our tracing of the rays by this first intersection, but we can, against the normal vector, we can actually emit a secondary ray, which is the reflection ray. So you can see here, this is the viewing direction, and this viewing direction is simply reflected by the same angle theta against the normal vector, and by this we generate the reflection vector. And then with this reflection vector, we will simply do the intersection test and perform the illumination of the intersected geometry, and then transfer part of this illumination onto our surface point from which our R vector is emitted. How do we calculate this reflection vector? This is easy because we know the viewing vector and we also know the normal. So if we perform the projection of the normal of the viewing vector onto the normal, which is this term, then we simply make it s twice as long, and therefore this will be like this would make it, if I draw this geometrically, so this is the projection of our viewing vector onto the normal vector, and I do it, and I add this this would be this projection twice as long. So this is 1 time, this is 2 times, this is the magnitude. And now, if I am subtracting from this vector a view vector, so from this position, I will be subtracting the view vector, I will end up with my reflection vector. So once again, I want to reflect against the normal. I am first projecting my view vector onto the normal, then I double its length, because this is what will happen if R plus V will be equal to 2 times Vn scalar product and on the normal vector. So this will be the magnitude of the unit size normal vector. So this R plus V is here. V is here. This is V. And this would be R. And this defines, as they are equally long, R and V, the same size of the projection. So twice the projection of the view vector onto the normal vector is the magnitude of the normal vector, which will be resulting from adding a vector R and vector V. And now if I subtract from this this normal vector, scaled normal vector, the V, I will end up with the reflection vector R. Once I have this vector, I can perform the intersection test with this so-called secondary rays, and then I can add the light contribution from this secondary rays onto my surface, which I am calculating the illumination for, which is here. So with this, I can achieve this kind of effects of reflection, similarly as color bleeding, but for very specular surfaces such as mirrors, I will be able to achieve these mirror-like reflections. And that is all. We have been talking about the ray tracing, which the simple form has the basic components of performing the ray definition for each pixel in our screen, and then intersection test with the scene. Then we want to evaluate the illumination at that position and also evaluate whether we are in shadow or not. And perhaps we are also interested not only in the shadows, but we are also interested in the reflections. And so in addition to shadow rays, we will be also casting from our surface points the secondary rays. This you can implement yourself, and this will be your first task on the assignment, which you will find in the Blackboard interface as the assignment number 1. And this, however, you can also achieve by a hardware acceleration. Just that you know, the graphics hardware, the GPUs, are currently also performing this ray tracing for you. So before you are able to enjoy this API on directly supported by the graphics hardware, it is important that you understand what is exactly happening, and for that it is important that you learn how it works and also exercise the ray tracing by the assignments. That is all from my side for today. Thank you very much for your attention.